Hello, everyone. This is Jason Flower, a partner in Husch Blackwell's Environmental Group. We are excited to welcome you today to the third installment in the Emerging Environmental Law Trends webinar series. We will be talking with you today about the U.S. EPA's definition of solid waste, the new regulatory framework for recycling hazardous secondary materials under the RCRA, and the EPA's proposal to modernize the RCRA Ignitability Characteristic, and trends and issues regarding remediation of two hot contaminants, quote-unquote, TCE and PFAS. Before we begin, I'll cover a few housekeeping items. At the bottom of your audience console are multiple icons for your use today. I'll highlight a few. If you have any questions during the webcast, please submit via the question box. We will try to answer all questions during the webcast today, but if a more in-depth answer is needed, or if we run out of time, it will be answered later via email. There is also an icon to assist you with your viewing preferences. As usual, I'm sure you're all used to this, you can expand your slide area by clicking on the maximize icon on the top right of the slide, or dragging the bottom right corner of the slide area. If you have any technical difficulties today, please click on the help icon in the top right corner. It has a question mark and provides information regarding common technical issues. A copy of today's slide deck is available in the resource list icon that looks like a folder at the bottom of your screen. This program has been approved for Colorado, Illinois, Iowa, Kansas, Missouri, Nebraska, Tennessee, and Texas continuing legal education credit. Ohio and Wisconsin CLE is pending. To report your hours in Illinois, Kansas, Nebraska, Tennessee, or Texas, click on the CLE widget at the bottom of your screen and complete the questions. You'll need your bar numbers to submit. A recording of the webcast will be available tomorrow for watching and sharing. Once available, a link to the recording will be emailed to you along with a certificate of attendance. So quickly today, I've just wanted to show the slide with the overview. We'll talk about solid waste. We'll talk about hazardous waste recycling rules. We'll talk about the ignitability characteristic, changes to that, and then an update on, as I said, the emerging contaminants. Although TCE is probably not an emerging contaminant, but there have been some changes in that area. Joining me today are John Osborne of GZA Environmental and my colleague Megan McLean. John Osborne is a principal hydrogeologist and senior vice president in the Milwaukee area office of GZA. His areas of specialization include developing risk management and remedial strategies for legacy sites throughout the United States, the closure of such sites requiring strong geological and hydrogeological site characterization, and the development of defendable conceptual site models, CSMs, that are used in understanding the complexities of contaminant migration, including the emerging contaminants we'll talk about today. And he's also involved in selecting remedial solutions that balance both risk and cost. In his 25 years with GZA, John has managed and directed a large and diverse portfolio of sites implemented by teams of engineers and scientists at GZA. And he has taken active roles in representing clients and negotiating technical issues with U.S. EPA, Department of Justice, state regulatory agencies, and also represents clients on litigation matters. As I said, John is in Milwaukee, and he's based in Wisconsin, but he is responsible for GZA's consulting practice throughout the Great Lakes states. As some of you may know, a few years ago, Husch Blackwell, my firm, merged with White Hirschbeck Dudek in Milwaukee, Madison, and Wisconsin. And so I'm particularly happy that John could join us for this CLE, given his relationships with my Wisconsin colleagues, including Phil Bauer, and his location in Milwaukee. So we're kind of expanding the group here. Second, I'm happy to introduce Megan McLean. She's a third-year associate in the environmental group in St. Louis. Megan combines her passion for the environment and skills in environmental law to handle key client issues, including environmental permitting and compliance issues, complying with state and federal environmental laws and regulations. What I understand next is that because we have some Kansas folks on the line, we have to ask some poll questions. So I'm going to click through the poll questions, and you all, I understand, can click on your screen and answer the poll questions. They're simple. This won't be difficult. First, I work in the following industry: real estate, manufacturing, energy, environmental consulting, insurance, finance, healthcare, IT, retail, academia, legal, other. So please click on the one that sounds best for you. All right, looks like we have some consultants on the line. Welcome, guys and gals, and some other folks. We appreciate you being on. All right, again, Kansas makes me do this part. Have you attended one of our other webinars on regulations governing disposal this year? Please click the answer that works for you. And that looks great. I'm happy that some of you were on the AIR webinar, and I hope you enjoyed it. I know Phil Bauer and Allie did a great job. All right. How often do you work with facilities that are registered hazardous waste generators? I assume everyone can read the answers. All right. Frequently. That is good. I'm glad you all have self-selected yourself for this program. All right, with that, I'm going to hand the reins to Megan McLean, who will provide some timely updates on RCRA issues before John and I come back and address the emerging remediation issues involving TCE and PFAS.
All right, so the Resource Conservation and Recovery Act, also known as RCRA, was passed in 1976 and created the framework for America's hazardous and non-hazardous waste management programs. Materials regulated by RCRA are known as solid waste, and under RCRA, EPA developed detailed regulations that define what materials qualify as solid waste and hazardous waste. As you can see from the flowchart, only materials that meet the definition of solid waste under RCRA can be classified as hazardous waste and subject to additional regulation. As a result, understanding the definition of solid waste is an important first step in the process EPA set up for generators to follow when determining if the waste they generate is a regulated hazardous waste. So, there we go. So first off, it's important to note that solid waste is not limited to wastes that are physically solid. Many solid wastes are liquid, semi-solid, or contain gaseous material. Under the regulation, a solid waste is any material that is discarded by being abandoned, inherently waste-like, recycled in certain ways, discarded military munition. The term abandoned really just means thrown away. A material is abandoned if it's disposed of, burned, incinerated, or sham recycled. In addition, some materials pose such a threat to human health and the environment that they're always considered solid waste. Examples of these inherently waste-like materials include certain dioxin-containing wastes. Materials are recycled if they're used or reused, for example, as an ingredient in a process, if they're reclaimed, or if they're used in or on the land in a manner constituting disposal, burned for energy recovery, or accumulated speculatively. So I'll also note that some of the materials that would otherwise fit the definition of solid waste are specifically excluded under the regulation. So if we go back to EPA's flow chart, you can see that once you have a handle on whether the material you're generating is solid waste, the next question is whether the waste is excluded from EPA's definition of solid waste or hazardous waste. Many of these exclusions are mandated by RCRA, but many exist because EPA concluded that these materials should not be regulated as solid or hazardous waste for policy reasons. For example, several exclusions were designed to provide incentives to recycle certain materials, or because there was not enough information on the material to justify its regulation, or simply because the material was already subject to regulation under another statute. So in order to encourage recycling, EPA issued 3 rules from 2008 to 2018. Collectively, these rules are known as the definition of solid waste rules. And specifically, they codified 3 exclusions to the definition of solid waste for hazardous secondary materials that are reclaimed. And while 10 years may seem like a long time to issue these 3 exclusions, the reason it took so long was, of course, litigation, which culminated in July 2017, March 18, and July 2019 decisions by the DC Circuit, which we will talk more about. So the first of these exclusions is the generator-controlled exclusion. And because the hazardous secondary materials here remain under the control of the generator from the point of generation through completion of reclamation, EPA is fairly confident that there will be minimal mismanagement or discard of these materials resulting in a threat to human health or the environment. So this under the control of the generator exclusion actually consists of 3 options. Under the first option, materials generated and reclaimed at the generating facility, which must be located in the U.S. or one of its territories. So here, even if a generator contracts with a different company to reclaim the hazardous secondary materials at the generator's facility, either temporarily or permanently, the materials are still considered to be under the control of the generator. So for example, spent pickle liquor is oftentimes reclaimed at steel plants by companies that are different from the company operating the plant, and this is still considered to be under the control of the generator. The second option is where material is generated and reclaimed at different facilities, both of which are located in the U.S. or its territories, and both of which are controlled by the same person. So for purposes of this option, control just means the power to direct the policies of the facility, whether by ownership of stock, voting rights, or otherwise, but it does not include contractors who operate facilities on behalf of a different person. So here, EPA is looking at who the owner of the facility rather than, or more than, the operator. And where the hazardous secondary material is generated and reclaimed at different facilities, the generator is required to certify that the facilities are under common control and that one of the facilities has taken on full responsibility for safe management of the secondary hazardous material. Under the third option, the material is generated pursuant to a written contract between a tolling contractor and a toll manufacturer, both of which are again located in the U.S. or one of its territories. Here, the tolling contractor is just a person who arranges for the production of a product or intermediate product by the toll manufacturer. And so here, the toll manufacturer produces something and it goes straight to the tolling contractor who reclaims it, and then the material can then be used. And it can't be used as a product supplied to land or as a fuel. In addition, the tolling contractor has to certify that it has a written contract with the toll manufacturer to manufacture a product and that it will reclaim the hazardous secondary material. And it also has to certify that it will retain ownership of and liability for the hazardous secondary material that's being generated during the course of the original manufacturer, including any releases of hazardous secondary material that occur during that manufacturing process. So next we have the transfer-based exclusion, and this exclusion is the one that has been subject to the most litigation, but was recently upheld by the DC Circuit in July 2019. So this exclusion is for hazardous secondary material that's transferred to another person or a company, either foreign or domestic, for reclamation. So importantly, these facilities do not need to have a RCRA permit or an interim status in order to store or reclaim these materials. The generator can send these secondary materials to an intermediate facility, which is allowed to hold the materials for more than 10 days before they're sent on to the reclaimer. The reclamation facility then reclaims the materials at the site, producing a reclaimed material that can be reused at the generator or the reclaimer's facility or sent to a third facility for use. However, there are some limitations on how this material can be used. For example, it again cannot be used to produce a product applied to land or as a fuel. In addition, it's important to note that oftentimes there will be some residue generated in the reclamation process. Assuming this residue will be discarded, they are considered solid waste, and if they're hazardous, they actually do have to be managed as hazardous waste under RCRA Subtitle C. So because under this exemption, the generator has relinquished some control of the material, EPA believes several conditions are needed under this exclusion in order to ensure that the hazardous secondary material will not be discarded. First, the generator must make reasonable efforts that are repeated, documented, and certified every 3 years to ensure that each reclaimer will legitimately recycle the material and that any intermediate facility and reclaimer will manage the material in a manner protective of human health and the environment. So a generator can use any credible evidence in making its reasonable efforts, including information gathered by the generator, such as during an audit, provided by the reclaimer or in the intermediate facility, or provided by a third party. So for example, hazardous secondary material generators oftentimes hire an independent auditor to review the operations of the reclaimer, obtain audit reports from a consortium of generators, or rely on an assessment of a recycler or intermediate facility made by either a parent corporation or a trade association that is used by a group of generating facilities. I'll also note that these reasonable efforts are not required where management of the material is addressed under a RCRA permit or interim status standards. Lastly, although the reclaimer and any intermediate facility do not need to have RCRA permits under this exclusion, they still must obtain financial assurance similar to that required for permitted TSC facilities. So the last exclusion is the remanufacturing exclusion, and this allows the transfer of certain spent solvents from one manufacturer to another for remanufacturing, which is just extending the useful life of the original solvent for recycling the spent solvent in a manufacturing setting. This exclusion does not apply to spent solvents sent to commercial recyclers. It's only available for transfers of these spent solvents within the pharmaceutical, organic chemical, plastics and resins, and/or paints and coating industries. As you can see in the diagram, this exclusion is similar to the second form of excluded recycling that is under the control of the generator. So that was the one where materials are generated and reclaimed at different facilities. But here, because there's no requirement that the manufacturing exclusion, or here there's no requirement in the manufacturing exclusion that the generator and remanufacturer would be controlled by the same person. So as a result, EPA requires the hazardous secondary material generator and the remanufacturer to notify EPA of the remanufacturing and to develop and maintain an up-to-date remanufacturing plan. So this plan should include the types and estimated annual volumes of spent solvents to be remanufactured, the processes and industry sectors that generate the spent solvents, the specific uses and industry sectors that'll use the remanufactured solvents, and a certification from the remanufacturing stating that it will accept the solvents, and that it will remanufacture the solvents, and that it's equipped with air emissions controls that will enable it to comply with appropriate Clean Air Act regulations. So, once you've concluded that your waste meets the definition of solid waste and does not fit into one of the exclusions, either ones we discussed or any of the other exclusions enumerated in RCRA's regulations, the next policy is whether or not your waste is hazardous. Under RCRA, solid waste are classified and regulated as hazardous waste if they are explicitly listed or if they exhibit a characteristic property of hazardous waste. So there are 4 such characteristics: ignitability, corrosivity, reactivity, and toxicity. So the ignitability characteristic is the one that EPA is proposing to change, so that's the one we're going to focus on. And as written right now, it specifies that the following categories of solid waste qualify as hazardous: liquids with splash points below 60 degrees Celsius or 140 degrees Fahrenheit, except for aqueous liquids with less than 24% alcohol; non-liquids that are capable under standard conditions of causing fire through friction, absorption of moisture, or spontaneous chemical changes, and that, when ignited, burn so vigorously and so persistently that they create a hazard; ignitable compressed gases; and oxidizers. So in April of this year, EPA proposed a couple of changes to this characteristic under RCRA, And these changes could cause more waste to be classified and regulated as hazardous waste under RCRA. So the first of these changes would apply to exclusions of aqueous alcohol waste. EPA originally established the exclusion for aqueous liquids with less than 24% alcohol to ensure that certain wastes like wine and latex paint that have low flash points but are unable to sustain combustion are not classified as ignitable hazardous waste. Now EPA is proposing to change the exclusion so that it applies to alcohol-containing solutions with at least 50% water rather than aqueous solutions as under the current regulations. So this is a little bit more specific than the previous regulation. And in addition, they're also proposing to add an exception for the exclusion in circumstances where the alcohol has been used for its solvent properties and is one of the alcohols specified in EPA hazardous waste numbers F003 or F005. This proposed language has been interpreted to suggest that whenever an alcohol specified in either of these listings is used for its solvent properties, the resulting waste will qualify as a hazardous waste. In the past, EPA has always maintained that these listings do not extend to certain wastes where a listed chemical was used for its solvent properties, such as commercial products with solvent ingredients like ink for paints, or processed wastewater contaminated with solvent constituents, water used to clean equipment that has solvent residues from an initial solvent cleaning operation. So the other proposed change is a new provision stating that multi-phase mixtures are ignitable if any liquid phase in the waste meets the criteria for an ignitable liquid, or if any non-liquid phase meets the criteria for an ignitable non-liquid. So this is interesting because multi-phase mixture is not defined in the proposed regulation, so it's unclear whether an article that consists primarily of solids with a small amount of liquid firmly embedded inside of it, like a capacitor with dielectric fluid or a small battery with an electrolyte, would be viewed as a multi-phase mixture, or whether it be viewed as a solid under the new regulation. So the comment period for this proposed rule closed this summer, so we'll have to wait and see what happens with the final rule.
All right, thanks, Megan. That was great. All right, so on the second sort of half of this, we are going to switch gears. We were thinking about, what might be of interest to folks. And so the topics we're going to cover are kind of remediation and quote-unquote emerging contaminants. In my practice, I've seen a lot of interest recently or sort of issues arise regarding TCE and PFAS, PFOA. I think everyone's hearing about PFAS and PFOA, and some are dealing with TCE issues. So I'll give a quick overview of kind of just set the table, and then John Osborne will discuss the technical remediation implications for both of these contaminants, and kind of for TCE, where sites stand and how we might move some of the legacy TCE sites forward to closure, and then for PFAS, kind of what we're worried about, or kind of how do you test for it, and given the characteristics or the levels that have been set. And also what I think is on a lot of people's minds is, if I have a site like this, what do I do with it, and how am I gonna, how are we gonna move those sites forward? So TCE, trichloroethylene, historically widely used as a solvent degreaser and chemical intermediate. You see a lot of sites with heavy degreasing, historic degreasing issues, or operations with TCE contamination. TCE has mostly been phased. It was also used in some products, even some consumer products and dry cleaning, spot cleaning. Mostly phased out, but still a COC contaminants concern at a lot of manufacturing and disposal sites, landfill sites. historically, most of those sites were driven by a drinking water concern. So if you could rule out a drinking water pathway, you could pretty much, kind of deal with the site. But the agencies have been focused recently on vapor intrusion as a potential exposure pathway for TCE. Along those lines, in 2011, EPA updated the inhalation reference concentration for TCE from 10 parts per billion to 2 parts per billion. Pretty big change. And it changed sort of the indoor air analysis significantly. And so that led to increased scrutiny of VI issues, vapor intrusion issues at existing sites. So what I've been dealing with some is kind of occupational worker exposure issues at sites and adjacent areas. The EPA regions and state agencies, after EPA changed the reference concentration, have been applying varying standards for indoor air, ranging from sort of 2 parts per billion to around 20 parts per billion. Also, obviously, dependent on whether you have residential or commercial, property type of commercial industrial exposures. In Missouri, DNR has been focused on a 7 parts per billion indoor air threshold for workplaces. And this isn't like all workplaces. It's only workplaces near a site or a Superfund site. And they've been focused on 2 parts per billion for residential properties near Superfund sites. So obviously those are very low levels. In comparison, OSHA's PEL for workplace air for TCE is 100 parts per million, which obviously that's significantly, way higher than what EPA has been looking at. But some of the OSHA folks would say that's probably outdated, and Cal OSHA and I think the AICGH have been kind of looking at 25 parts per million, but that's still, way higher than what EPA and the state agencies have been looking at and sort of, I won't say enforcing, but what's driving their decisions at sites. So agencies are revisiting sites and pursuing indoor air monitoring and potential vapor intrusion mitigation options. So, and this also, as I noted, has affected neighboring properties, including residential and general commercial properties, even strip malls, things like that. And I have represented both, site RPs with TCE issues, as well as some neighboring commercial property owners, and thought everyone could benefit from sort of a deep dive on TCE and remediation technologies, which is what John will do. Moving to PFAS, PFOA. Well, it's a water and oil repellent chemicals. A lot of people know that these chemicals were used in Teflon coatings. Something that I wasn't as aware of but have learned is that they were used in firefighting foams at airports and military bases where they did firefighting training. So that's been a focus. And if like for example, in California, they're planning on testing basically every airport and military base for PFAS in the groundwater, and also basically everywhere else in California. We'll see what happens. PFOA, PFAS have been used in carpet, textile, and leather treatments, and semiconductor manufacturing and cleaning products. This isn't a comprehensive list, but that's some uses. They are environmentally persistent and water soluble, concentrate and bioaccumulate, The issues are kind of occupational drinking water and oral dermal contact exposure. ATSDR and international groups have been conducting toxicological reviews lately, well, over the last about 10 years, but everything sort of seems to be coming to a head now. In April 2019, EPA published an interim proposed 70 parts per trillion preliminary remediation goal for PFAS in groundwater. I have to admit I haven't monitored the comments on that, but that's their proposed remediation goal, preliminary remediation goal. And then in the states have been applying widely varying groundwater screening and action levels, including down to 8 parts per trillion in Michigan, which is pretty astounding, I'll say. So PFAS is a hot new contaminant, and again, John will talk about, I'm going to kick it over to John to talk about, obviously this is all site-specific inquiries, and you have to look at what your site is, but he's going to discuss some of the general issues with PFAS, including remediation technology options or the current thinking on those. So I'll flip it to John.
Okay, good afternoon, everyone. Again, John Osborne with GCA. If you're not familiar with our firm, we're about a 55-year-old firm based out of Boston, about 32 offices. What I'm sharing with you today really is kind of collective experience we've had on TCE initially, because that has clearly been around a long time. We've got a lot of experience on that. We have more of evolving remedial technologies that show both success and maybe lack of success in some cases, and then to contrast that against PFAS contamination, which is kind of in its infancy in looking at remedial technologies and seeing what works. So we're going to kind of contrast these two compounds. They have a lot of potential for expensive site cleanups, so they have some commonality. To step back for just a minute, I just want to review kind of the relative distribution of certain compounds in the environment as a release, for instance, from an industrial site. We're simply looking at a case here. There's a kind of a large industrial property on the left-hand side of the screen. And if you're looking at hydraulic oils or PAHs, these are heavy oil type contaminants. Those contaminants stay pretty closely to absorb onto the soil matrix closely, and they don't result in a large contamination plume that is significant typically. They tend to stay localized. And I just want to contrast against having appreciation for, again, some of these more recalcitrant or problematic compounds. But if we add, for instance, a petroleum VOC plume coming out of an underground storage tank from heating oil or gasoline storage, for instance, where you have BTEX, I mean, those hydrocarbons also tend to, they can be more problematic, especially if you have free product. But in the main, a PVOC plume, petroleum compounds tend to biodegrade readily, and typically their plumes don't get too much larger than 200 feet, 250 feet. If you look at the literature, this is taking out of some American Petroleum Institute research, but this is pretty solid. And you'll find environments where this won't happen, but this is kind of the relative strength of plumes related to release. When you get to TCE, you get a much more mobile compound, and you also get additional characteristics of that plume which make it more concerning for us. As you look at this plume coming off, you'll see it's migrating underneath residential and industrial areas, and that, as Jason was referring to, the vapor intrusion issue becomes significant, because not only are you looking at potential direct ingestion, but you're looking at inhalation issues related to a fairly low level indoor air threshold for TCE. So just considering that background, we'll look at TCE and what are we learning from the sites we've been remediating. And I'm hoping you'll gain some perspective. I'll try not to get too much in the weeds on this and try to stay general, but you'll get all these slides with the words, and I'm hoping that it could be an ongoing resource for you. But TCE challenges have existed as far as bringing sites to closure. I mean, there's a lot of remediation effort out there, but the number of sites coming to closure is much more limited. And we've got industrial clients who've got TCE sites on their legacy list. They're continually refreshing those balance sheets, the financial reserves related to those. And we're in the business of closing sites out. We're not just about remediation. We need to bring sites to closure. So I really want to focus on that. In looking at TCE, just reviewing the characteristics so you appreciate the challenges sometimes that we face. TCE is both mobile and groundwater systems, which result in this fairly extensive plume that I just depicted, but it also sorbs onto the soil matrix. So you get distribution in groundwater, but what's being left behind, especially old plumes. I've got a site remediating right now, and we're finding that what we're seeing in the dissolve phase in the groundwater plume is when you measure groundwater samples coming out of a monitoring well, those concentrations really represent about 10 to 15 to 20% of the total TCE mass that's right there, because there's so much TCE sorbed out of the soil matrix around the groundwater. So when you address just groundwater, you're not dealing with the sorbed component, which can be very significant. When you're looking at free-phase TCE, what we call DNAPL, dense and aqueous phase liquids, this is where a spill may have occurred from degreasing solvent right onto the ground, over years maybe. And what's interesting about free-phase TCE is that it's hydrophobic. It really doesn't like water, but it's migrating out of gravity. It's more dense than the water. When it hits the water table, it really doesn't want to push through, except for the gravitational attraction or the head that's behind it. In other words, as it's trickling down through the soil, it eventually pushes through the water table. And then the next TC that's coming down wants to follow that same pathway because it's pushed the water out of the way, and you end up getting more of a dendritic, erratic pattern in the subsurface, which can be difficult to characterize. Interesting, TCE is subject to biodegradation, which helps us out, similar to the petroleum VOC plume, but it only really degrades in an anaerobic environment, in the absence of oxygen. So that has to be created, or you need to run into a natural environment that allows that anaerobic environment to be established. You also need to understand that biodegradation can produce toxic byproducts. So incomplete biodegradation, you could actually enhance the kind of the toxicity or the hazardous nature of a plume. And again, the TCE volatility, as Jason mentioned, is really low. The volatility is a concern simply because the indoor air thresholds are as low as they are. There was a recent study just a couple of years ago on fetal development concerns that sent a lot of shock into US EPA particularly, and ATSDR that set some of these standards. And as a result, they're still trying to replicate that study, but there continues to be a concern regarding cardiac malformations, which people are watching as far as TCE vapor inhalation thresholds. So I think the effects of TCE, the health effects, are fairly real and documented. They're listed here. So again, it continues to be a significant problem for sites that have significant TCE plumes. We started offering something a number of years ago called the Second Opinion Program, and a lot of what we're seeing and I'm presenting to you came out of our reviewing a number of sites where either consultants or RPs had gotten to a point where they weren't bringing a site to closure. They're paying for annual O&M in the tune of six figures, over $100,000 a year or more, and they weren't seeing a pathway to closure. So our review of these sites, I'm just going to kind of share with you what we've seen as we go through these. But the first thing is kind of a poor and incomplete CSM, or conceptual site model, and that's kind of terminology that the industry has acquired over the years, and a lot of consultants will talk about having or developing a CSM. EPA's definition is that it's not a digital model, or it's not a computer flow model or groundwater model, which you're maybe familiar with, but it's, as EPA defines it, the CSM is used to organize and communicate information about site characteristics. It should reflect the best interpretation of available information at any point in time. As a consequence, if new data is inconsistent, either the data needs evaluation or the model needs to be revised. And that's an important aspect of this. Another perspective of the CSM definition is that it's a coherent and systematic understanding of all major environmental factors that control the fate, exposure potential, and regulatory risks related to contamination released into the environment from source zone to down gradient receptor. So it's really understanding, hey, what does the source look like? Do we really understand source? Because that's where much of the mass of the contaminants tied up. Now it's being migrated from that source through various channels. Do we understand all of those, what the rate of migration is, what the rate of absorption is, and where are our risks related to down gradient receptors? Are the residential properties down gradient? Is there water supply wells? Where are they located? There's a myriad of those details which really need to paint the entire picture and really set the stage for a strong remedial strategy. Another thing we've seen that really prevents sites from being closed is kind of a lack of a source definition. We've seen a lot of expensive technology being applied, but not necessarily in the right location. And it often leads to this concept of what's the mass distribution. The question is, when you look at the TCE mass, there needs to be an accounting of some respect, a quantitative effort to look at where's the mass distribution. In other words, we've looked at sources, and we may come up with a calculation that says, in our source zone, we had an old degreaser beneath an industrial plant. We look at the soil impacted with kind of DNAP around this degreaser. It accounts for about 97% of the contamination. When you look at the down gradient plume, which everybody's concerned about, it represents about 3% of the released mass. That's an important factor when you're looking at what am I going to spend my effort on remediation. If you have a remediation technology that's only going to get you about 50% mass reduction, I hope you're not spending too much money, because with 50% of the mass out there, you're still going to result in a significant groundwater plume. So the understanding that mass distribution is critical to figuring out what technology is going to remove as much mass as possible, and am I moving the mass that is actually going to give us the biggest bang for the buck. Three-dimensional groundwater flow often lacks understanding. There's migration characteristics in the plume that people don't pick up on. That's pretty common. Small hydrogeologic variabilities can cause plumes to either deepen at distances or even change flow direction. Those are all complicating factors. So here's a list of kind of common remedial technologies. I pulled this out of the ITRC, which is a common consulting industry and regulatory industry consortium. And, just looking through these lists of typical methodologies, I'm going to talk about a few of them specifically, but you've got bioremediation technologies, flushing and surfactant technologies are looking at trying to mobilize the contamination, especially that sorbed phase, and try to remove it. In situ oxidation has been around a long time. Of course, monitored natural attenuation, most of you have heard about. It's really monitoring and hoping that there's natural processes reducing that plume. Source area excavation disposal, of course, when we're talking about mass removal, that's very quantifiable. We can figure out exactly how much we're getting out of the remediating from that site through that process. Phytoremediation has its applications, limited, but it has some applications. Things like steam injection, in situ electrical heating. There's some nanoscale technologies I'll talk about. Soil vapor extraction has been around a long time. You see less of that these days. And then reactive barrier walls. This is kind of doesn't encompass everything, but it encompasses many of them. I'd like to just touch on a few. So, and I'm really talking about kind of non-governmental sites. These are private sites that most of us tend to work on. In other words, the budgets are limited. We need to be effective and efficient. But the one thing I'm going to promote is the method of what's called EZVI, which is zero-valent iron, emulsified zero-valent iron. And it came out of NASA's development of actually trying to clean up their huge TCE plume at the shuttle launch pad. And really to develop this method that sequesters the TCE that doesn't like water, but it pulls it into an oil water emulsion and is actually abiotically transforms it in a relatively small period of time. And I'll point to the fact that the costs are less. We've seen situations where the costs are less than 50% of actually dig and haul when you're dealing again with the source zone, because picking up that source, going back to what Megan was talking about, if it's characteristically hazardous and you need to dispose of it as a hazardous waste, then the cost to do that is exponential compared to a solid waste. So an alternate is in situ treatment of that material through this process, and we've seen costs per cubic yard that are essentially less than 50% of dig and haul. So it's a very promising technology. Bioremediation and enhanced reductive dechlorination. We're seeing this as a lot of consultants on the phone right now, and a lot of us are seeing very effective, well-designed, and well-implemented and monitored bioremediation is very successful. It doesn't happen overnight. You need more in terms of years to kind of see the effectiveness of this methodology, but it depends on what your remediation goals are. I will say there's a range, and this technology is developed in a point where we have tools for where you have fast-moving groundwater, and really, let me just step back and say that what we're trying to do with bioremediation, because TCE doesn't like oxygen, we need to create an anaerobic environment. So we need to remove the oxygen from the groundwater system that would normally be there, and we need to provide an environment where these bacteria love to proliferate. And the other thing we're doing is we're adding culture these days. For initially, there was a lot of effort to just kind of develop the bacteria that's naturally present, and in a lot of cases those bacteria are present, but they're not present in enough populations that we like to, especially for kind of kicking off a process once you start injecting this material. So it needs to be enhanced with active cultures, and that doesn't cost that much. Something in the range of maybe 10% of the injection costs would include adding active culture. We just did a fairly large plume, about $200,000 to do a bioremediation injection, with about $20,000 for the active culture, and we're seeing a high success rate with that. We talked about monitored natural attenuation. Just a concern there is that we simply have enough to move the contamination from TCE to its daughter product of DCE, but not enough to move it all the way to ethene, where it is going to fully degrade. Now, in some cases, all you're interested is seeing TCE drop because maybe your vapor intrusion thresholds will now be attained. So it really depends on the application. In situ oxidation, we've seen problems with this. Generally, there's a lot of rebound. The graphs on the right kind of talk about or show the evidence of injections and showing initial results, positive results of chemox, but then rebounding concentrations through time, indicating that we're just not oxidizing enough material during this process. Understand source area excavation. Again, soil vapor extraction has its role. And I'm going to mention in situ electric heating or in situ thermal remediation. And I'm just going to mention the fact that if you're dealing with a TCE source that's in a very low hydraulic conductivity environment, clays, and maybe those clays have a lot of TCE tied up in it, but enough of it is bleeding out into a higher K zone beneath it and resulting in a down gradient plume, you might need to address it, and this is one of the ways, especially if it's beneath the building or difficult to get access to. And I'll mention barrier walls, but I'll also just kind of jump to a graphic here, which is an actual site where we had to address a chlorinated VOC plume underneath the building. What you're looking at in the upper left is really what's the heater wells that were installed to actually drive the TCE to the vapor phase and then vacuum extract it. And so that occurred beneath the building. If you jump down to the lower right figure, that's the tip of the plume. You'll see it's heading underneath the railroad tracks, which we couldn't get access or approval to actually do thermal remediation beneath that. So we switched to an ERD, or an enhanced bioremediation of the initial green probes actually providing that. Further down gradient, there's a whole set of probes which are actually an active barrier wall using a technology called plume stop, that if there are dissolved phase constituents that are leaving the plume, we have a third kind of belt and suspenders. So it's a good example of how you kind of bring technologies together to effectively remediate the site. Now, I will mention that we have about 99% reduction of TCE, especially in the DNAPL or a high contaminated source zone. So just summarizing TCE, they need to be founded on a solid CSM. It's worth investing in understanding if there is DNAPL present and understanding kind of the configuration of your source. We also need to, look at a solid remedial action plan that looks at long-term risk and liability and balances those issues. You want to understand what longer-term risks you might have. If you don't want to spend money now, that makes sense, but are you exposing yourself down the road? Vapor intrusion concerns in our neighborhoods. We've had a number of neighborhoods where we've done exhaustive vapor intrusion mitigation, and it's worked very successfully. Neighbors have gone along with it. In some cases, we have found, we're in a mix of litigation right now because there's class action lawsuits out there. I'm sure some of you have seen both of those occurring. So it makes sense to mitigate that to the extent as quickly as possible. It doesn't cost that much to mitigate, especially residences, and it makes sense to deal with that. And I just mentioned again, remediation is often iterative. It often requires multiple levels of remediation, depending on site complexities. We're going to shift over to PFAS, and as another recalcitrant compound that we're now dealing with. And I'm going to talk a little bit, and I'm going to speed things up a little bit as we go through this. And again, the slides are available for you, so you could take a little bit longer to look at this. But when putting this, PFAS into context with TCE, TCE gives us enough problems of its own. But if I theoretically apply, a PFAS plume to this particular diagram, PFAS is going to be way out in front of the TCE. It's much less retarded by adsorption to the soil matrix. And, what this is trying to depict is, it's gotten to the river down gradient, and not only is it's now discharging essentially in some concentration to that river. It's absorbing onto some sediments, and so there's some adsorption there, but it's also introducing itself to the ecosystem of that riverine environment. So you have complicating concerns with PFAS simply because of its vast mobility. Some consultants and hydrogeologists are talking about it as the ultimate tracer. In other words, you want to figure out where groundwater flows. Look at your PFAS plumes. I'm going to emphasize data, field sampling care and making sure that data quality is there. Laboratory data is so critical in PFAS if you're going to test. And a lot of decisions are being made on very small quantities of contamination. And I'm providing this perspective from a firm that's collected over 10,000 samples for PFAS right now. But it comes down to this low-level detection. The 70 parts per trillion. That's 1 second. Well, 1 part per trillion is 1 second in about 32,000 years. It's surprisingly an infinitesimally small quantity for us to quantify. So the potential for high cross-contamination from consumer products that carry these is extremely high. Again, we lack numerical standards for PFAS in some states. Some states are developing them. There's variation in analytical techniques. And there's PFAS represents a very complex mixture of compounds that are very difficult to quantify. And again, you're sampling in an environment where PFAS has been around for a while, and it's liable to be distributed in the environment. As Jason mentioned on the front end, very mobile. They don't volatilize. There's new information in biodegradation, which is coming out right now. But in general, unless you introduce some of these microorganisms, you're not seeing biodegradation. Selectively absorbed, And again, they've been distributed in our environment for a long time through wastewater discharge, through industrial air emissions, both regulated and unregulated landfills. So it's been around a long time, but we haven't been testing for it. And I've seen people say, PFAS has got to be ubiquitous, and in some cases it is. It's in human blood. But I would say based on sampling, it's not everywhere, but where it has been used or placed, it's widely distributed. When you're talking about a sampling plan, I'm just going to touch on a few items here, but consider what your objectives are. What's the endpoints? How's the data going to be used? Do you understand the media that you're targeting for sampling? Do you understand what the specific source of PFAS is? Or are you looking at a forensics that kind of characterize what that source is? Is the media stagnant, or has it changed character, for instance, a wastewater stream? Understand who's performing the sampling. Do they have experience in this? Does the laboratory understand, and out of the experienced laboratory? We have about 4 pre-qualified laboratories that GZA is using right now in the country. More are coming online, but not everyone has an appreciation for the level of QA/QC required. And a number of things here related to just understanding the data. And really the last point there, just, do you have a plan in place once you have the data in hand? Going into the field, I just want to say, a number of the consultants that are doing this kind of work, we have a very rigorous SOP that we didn't have to have, or even TCE. But our field teams go organic for basically 48 hours beforehand. No personal care products, no fast food, because fast food wrappers, again, have PFAS coatings on them. No synthetic clothing. And we've overhauled all of our field equipment and removed anything with PFAS. If we couldn't identify whether it had it or didn't have it, we removed it. But if you stand up before the public and you've got 30 parts per trillion of PFOS or PFOA in their water supply well, you better be confident about the data. And you don't want to be, responsible for introducing such a low quantity inadvertently. That is clearly a concern and something that needs to be taken seriously. I won't go much on the laboratory methods other than to state that the 537 method is the current adopted method, and it's being modified by a lot of laboratories in order to get, it's a drinking water test. So in order for you to test water out of a monitoring well, which maybe has other things in it, it requires some modification. Not all labs do that the same, so there's some variabilities which are, EPA doesn't like that, and the states are trying to deal with that. Let's talk about soil remediation. There isn't a single silver bullet for soil remediation. We're talking about excavation and landfilling. This isn't very high tech, but that's what we're looking at sites where you can at least remove the source material related to PFAS. Again, you're transferring the liability to a landfill potentially. We've had some landfills push back on even receiving the material. So it does, produce a leachate, and that leachate retains some level of liability. So you need to be careful what facilities you're taking your PFAS impacted soils to. It's more suitable for low PFAS concentrations or smaller soil volumes. It really depends on site conditions. We're looking at soil containment and capping in place where you've got larger volumes and you're simply trying to prohibit surface infiltration from going into and mobilizing that into the water table. Of course, that includes engineering controls and some ongoing activities to make sure and ensure that those capping materials are both effective and in place for a long time. What about thermal treatment? I'd love to say that that's very successful, but temperatures greater than 1200 C are needed. I've heard of temperatures up to 1800. So that results in a very expensive and costly approach. I'm not even going to talk too much about the soil absorption and stabilization methodologies. I mean, some of you are familiar with in situ stabilization. Because of the mobility of PFAS, it's yet to be proven that actually can be successful. Chemox, which is another methodology you'd assume might be applicable, has not proven so far. So a lot of treatment is happening at the kind of at the point of use or the point of entry. We've installed over 500 point of entry systems in residential homes that they're treating the entire house. The great thing about PFAS is that it's treatable with with granular activated carbon relatively efficiently, and you can regenerate that carbon. It's reasonably effective. So we do have, this is one great thing about PFAS. There's point of use treatment as well, simply at the point of the tap. And you can use RO as well as what we refer to as GAC as well in that. And for water supplies, again, activated carbon and ion exchange resins are coming online as well. I see we're at 1 hour right now. I'm just going to try to finish up quickly, Jason. If you can hang in there.
I think this is great, John. I mean, if people want to drop off, they're welcome to. But I think you're going to wrap up pretty quickly here, and we'll be good. So.
Yeah, 3 more slides for anybody who's kind of wondering. But we're really back to pump and treat. When you're talking about now a contaminant that's mobile in groundwater, what are we going to do with it? We can't in situ. In some cases, it's been so mobile, it's quite deep in the groundwater system. So we're looking at large volumes of pump and treat again, like we were for chlorinateds back in the 90s. Something we steered away from, but for PFAS, because it is so mobile, it's appropriate. And then to treat it right now on the surface and possibly re-inject it, where states would allow that, or you'd have to discharge it. But that is definitely a viable technology, but you need to concern yourself if you are discharging to municipal sewer and what additional treatment may be required. In some cases, in order to do that, you need to do pre-treatment. You're bringing and blending waters together. It's just not as simple as running it through some large activated carbon. And of course, there's long-term maintenance, and it's not a simple venture just to go in and capture millions of gallons of water in a day and treat it. Again, chemical oxidation. I'm definitely seeing a number of technologies kind of on the bench scale. It's complicated, and it's really not proven yet for field applications. There's a lot of sorption. Besides activated carbon, there's a number of other materials being developed for absorption of compounds out of the water stream. Ion exchange resins, if you go to a conference on emerging contaminants, a lot of these guys will be there with their exchange resins. They look quite effective. I've seen comparative costs on these, and they're pretty expensive right now compared to activated carbon, but the prices are coming down, and depending upon the volume, they could be very applicable to certain situations. Most of us know RO is expensive, but it is out there. And just literally today, in situ biological degradation, really there's a lot of researchers looking at this right now. Came out in Environmental Science and Technology. But this a strain of bacteria coming out of a wetland in New Jersey, actually, Acidomicrobium A6, they found to actually defluorinate these fluorinated compounds quite efficiently in the range. They've been able to replicate it in the laboratory at about 60% mass reduction in about I think it was 8 weeks, something like that. But these bacteria they just discovered they're surviving on ammonium typically. So we may, this isn't the only strain that they're working on right now, but this one was just published today again. This would be great to be able to find an environment we could kind of create that environment subsurface and again have microbes that are effective at reducing these. So in conclusion, again, PFAS is widely distributed, creates some significant challenges for remediation, and we're really not looking at a silver bullet technology. There's a lot of things being talked about, and the technology is continuing to evolve. Again, activated carbon, very good. Realize that 20 states, as of this last week, I think it was, have developed either standards or action levels for PFAS. So the states continue to move ahead of EPA as they kind of grapple with what to propose for an MCL or consider this a hazardous substance. And just, if you suspect PFAS is on a site, plan on it being there, and if it's there, you're going to find that it's in groundwater, and you're probably going to find that it extends off the site already. I'm just going to tell you now, if it's been around too long, unless this is a brand new kind of release. Regions where groundwater is the source of drinking water are just showing up to be the highest liability for responsible parties. Not a surprise. A lot of litigation implications and third-party concerns over these issues, and there's been a high need for public relations in just kind of effectively addressing kind of public concern regarding this, because plumes are extremely large. I'll tell you, back in the home state here, there's one particular RP that's been just asked to investigate 3,500 acres of land that was used for land spreading of biosolids from a municipal treatment plant that received PFAS-impacted wastewater from this facility. So those biosolids went out to the agricultural fields for years, and the state regulatory agency is saying, please, we want you to investigate 3,500 acres. So that is a big deal. Jason, that is the presentation. Thank you so much for listening.
Thank you, John. I don't know if there are any questions. Now would be the time to ask them. You can click on the bottom thing that says Q&A and ask questions. Oftentimes we don't get a ton, but we are happy to answer questions. And otherwise, I would just say, I'll hold on. I will say thank you, John. Thank you, Megan. I appreciate you all being on. I thought that was really interesting. I think that, looking forward is where we need to be, and and I wanted to, everyone's hearing about the concerns, but it's helpful to start looking towards the future and how we're going to address issues. So everyone can drop off now. This is my moderator script closing. Basically, I'm required by the lawyers to do this part. But thank you all for joining our program today. We hope the information was helpful. If you have not already, please click on the survey icon on the bottom of your screen to complete our short survey. Your feedback would be invaluable for future programs. As a reminder, this program has been approved for Colorado, Illinois, Iowa, Kansas, Missouri, Nebraska, Tennessee, and Texas CLE. Ohio and Wisconsin CLE is pending. A recording will be available tomorrow for watching and sharing. It's emailed, I believe, to everyone who RSVP'd, and once available, a link will be emailed to you along with a certificate of attendance. Looking forward, please be sure to join us for the final webinar in our Emerging Environmental Law Trends series, or at least our series for this year, titled Regulations Governing Chemical Use and Manufacture. Thank you all again for joining us today. This concludes our webinar.